Hello everyone and welcome. In this video we're going to be discussing the rather unique opposed piston engine that Opposed-Power is developing, which has shown to have pretty impressive efficiency figures. Now the first opposed piston engines date back to the late 1800s, and they've seen use in ships, airplanes, submarines, tanks, trains, and other forms of transportation ever since. Rolls-Royce even developed an opposed piston engine for use in military applications in the 1950s. Having a look at the engine, you'll see that two pistons move towards one another, meeting at top dead center where combustion then occurs. These engines operate as two-stroke engines, meaning every single time the pistons join in the center, the power stroke occurs, unlike four-stroke engines. The basics of how this engine works is fairly straightforward. When the pistons reach bottom dead center, fresh air is pumped in through ports on the bottom of the cylinder, while the exhaust is pumped out through ports on the top of the cylinder. The two pistons then move towards one another, and just before meeting in the center, diesel fuel is injected directly into the cylinder. There are two injectors for each cylinder, both facing one another on opposite sides. Combustion occurs, pushing the cylinders back out, and then the cycle repeats itself. The top pistons and bottom pistons each rotate an individual crankshaft, and these two crankshafts are then geared together to supply power to a single output shaft. Now, while having two crankshafts may seem like an additional complexity, this engine has no valve train, meaning no camshafts, rocker arms, valves, valve springs, and even no cylinder head. This particular engine we're looking at is the Opposed-Power 2.7-liter 3-cylinder engine, which is good for 270 horsepower and 480 pound-feet of torque. What makes this design efficient? Well, with the lack of a cylinder head, the amount of surface area that the combustion is exposed to relative to the volume of the combustion chamber is significantly reduced. Instead of transferring heat to a cylinder head, that heat is sent to an opposing piston, so more heat is used to generate useful work. Also, by splitting the total stroke length between two pistons, you're able to have a very high stroke-to-bore ratio without super high piston speeds, helping to extract as much useful work as possible. It's also possible to create an ideal combustion chamber with both piston tops, helping to create a fast-moving mixture and quick combustion. The two-stroke engine is supercharged to control intake air pressure, and it's also turbocharged. The intake and exhaust ports are designed to optimize airflow scavenging. The exhaust ports are open first, allowing higher pressure exhaust gases to begin to exit. Once pressure has dropped, the intake ports are exposed and fresh air flows in while the remaining exhaust gases are pushed out. Both ports are closed off as the pistons move towards the center, and a small amount of residual exhaust gas is left behind. You might be wondering why the engine has specifically 3 cylinders. From an efficiency standpoint, this is found to be the ideal setup. With just 2 cylinders, there are gaps in exhaust delivery to the turbocharger, which reduces overall efficiency, especially at low loads and low engine speeds when you're not producing much exhaust. With 4 cylinders, there is too much overlap between the exhaust ports opening in one cylinder and the intake ports opening on a different cylinder. This results in additional residual gas being left behind, decreasing scavenging efficiency, which reduces overall efficiency. Now, that's not to say that the engine can't be used in other layouts. 2, 3, 4, and 5-cylinder options are all acceptable, and Opposed-Power has worked on developing a 4-cylinder engine for combat purposes, but from an efficiency standpoint, 3 cylinders remains ideal. Speaking of efficiency, test results show brake thermal efficiency remaining above 40% across a wide variety of loads and RPM, peaking as high as 46%. Indicated thermal efficiency doesn't dip beneath 51% for the various loadings tested. So the advantage here isn't just that the engine is super efficient, but that it remains efficient across a wide range of RPM and loading. Now, these efficiency numbers were achieved in 2012. Studies published in SAE as recent as 2017 have shown that brake thermal efficiencies as high as 55% are possible using 3-cylinder opposed-piston diesel engines. So the next and most obvious question, will we ever see these engines in production vehicles? Obviously, adopting new engine technologies can certainly be a risk, but we just might see them in the near future, as reports from the 2017 Detroit Auto Show indicate that 9 automakers have signed on as development partners, and at least one of them has started to implement tooling for producing an opposed piston engine in greater volumes. I'd love to hear your thoughts on this engine in the comments below. What do you think is good about it, and what flaws does this design have? What do you think is holding it back from mass production currently? Also, if you're interested in other unique engine technologies, I'll include links in the video description, as well as additional information about this engine. If you guys have any questions or comments, feel free to leave them below. Thanks for watching.